To start with this, let's review lemma. This is called the Genome Bound lemma. And this is a lemma about random variables. We are saying here that we have k random events, random variables. And here we're saying that maybe these events are not independent from each other. The Genome Bound tells us that the probability of the union of these k events is at most the sum of the probabilities of each of the events happening independently. So what we are saying here, the probability that all these events will happen is less or equal than the probability of event A1 happening plus the probability of event A2 happening, so on until the probability of AK happening. So the probability of any one of k events happening is at most the sum of the probabilities of the k different events. So this is one lemma that we are going to use later on to analyze the relationship between bias and variance. Another lemma that we will need is the hoeffding inequality. This lemma says, let Z1 to Zm be m independent and identically distributed random variables drawn from a Bernoulli distribution. So these IID conditions that all these m events are independent from each other and that are identically distributed. So they were generated identically in an identical process. These are one of the main conditions under which many theoretical results on machine learning have been proven. So this is a very important assumption. Usually we simply say we assume that these events are IID. So it means independent and identically distributed. So here we are assuming that these were events that were generated or drawn from a Bernoulli distribution. So this is the probability of Zi to be 1 is phi, and therefore the probability of Zi to be 0 is 1 minus phi. Now let this phi circumflex be the average of these random variables, or the mean of these random variables, and we define it as simple as the sum of these z variables divided by m. And let also this gamma number be a positive number and a number that is fixed. Then the hoeffding inequality says that the probability that the real phi is as close to the average or the estimated phi, that this distance between the real and the estimated phi is larger than gamma, this probability is at most 2 times the exponential of minus 2 gamma squared m. Okay, this is what the hoeffding inequality says. And if you remember, we saw this expression in the analysis of AdaBoost. And in that analysis, we saw that if you increase this number here, since this is a negative, as you increase this, the exponential of this will decrease. So, and in this expression, m, you will see later that this m would refer to the number of training examples that we have. And you will say that this will make reference to the generalization error and the error in the training set. Okay, so this lemma, which is also called the Chernoff Bound, say that if we take the estimated or the average phi to be our estimate of phi, then the probability of our estimate to be far from the true value is small, as long as m is large. Okay, so this is the way we can read this inequality. So using these two lemmas, the Genome Bound and the hoeffding inequality, we will prove some of the deepest and most important results in learning theory. In this analysis, we will restrict our attention to the binary classification problem in which the labels are 0 or 1. However, all this analysis can be generalized to other conditions like on problems like regression or for multi-class classification. As usually, we will assume that we are given a set of training examples, pairs of inputs and outputs, and we are considering m examples. And all these examples, we are going to consider them to be IID, okay, to be independent and identically distributed from the same probability distribution that we are going to call this probability distribution D. So for a hypothesis H, and hypothesis H, remember a hypothesis H could be, for example, a polynomial of degree 3, for example, with a specific parameters, theta. So for a hypothesis H, we define the training error, which is also called the empirical risk or empirical error in learning theory. We will define this error as this epsilon circumflex. So whenever you see an epsilon circumflex, we are talking about the error of a hypothesis H with the training set. Okay, this circumflex will make reference to the training set. So we can define this empirical error as the average of the points that were misclassified or that are misclassified by this model H. Okay. So this is just the fraction of training examples that H misclassifies. So if we have 1,000 examples and our H model misclassifies 500 out of 1,000, then we will have 0.5 as an empirical error. We also define the generalization error to be the error of that hypothesis H as the probability that this model will misclassify any pair of points that is drawn from the distribution D, which is the same distribution that was used for generating the training set. So this is the probability that if we now draw a new example from the same distribution D, H will misclassify. So this is the generalization error. Note that we have assumed that the training data was drawn from the same distribution D with which we are going to evaluate our hypothesis H. This is sometimes also referred to as one of the PAC assumptions. PAC comes from probably approximately correct. That's the way it is known, this framework, where we say that we are going to compute the generalization error using the same distribution that was used for generating the training set. So as an example, you can imagine if you suppose that you want to classify houses in houses that are expensive and houses that are not expensive in some city, then if you train your model with houses from this specific city, it only makes sense to apply this model to other new houses that are in the same city. So that's what we're saying here. We are using the same distribution D for the training of the model and for using this model in the future. So as I said, PAC stands for probably approximately correct, which is a framework and set of assumptions under which many results on learning theory has been proved. Of these, the assumptions of the training and testing on the same distribution and the IID assumption are the most important ones. So whenever we say we are going to prove this using the PAC framework, we are assuming that we are considering the same distribution for training and testing, and that we are considering that our examples were IID. Okay, so consider the setting of linear classification, and let this hypothesis h of x to be the dot product of the vector of parameters and the input vector. Then what would be a reasonable way to find theta, or to modify theta to fit the model, the points? So one approach is to try to minimize the training error. So we can try to minimize or make changes to our model in such a way that we get the minimum error, the minimum, this epsilon circumflex, this error with the training set. Okay. We call this process empirical risk minimization, and the resulting hypothesis output by the learning algorithm, we are going to call this H circumflex. So it's the best H, the best model that we can find that minimized the error with our training data set. We think of this ERM as the most basic learning algorithm. And algorithms such as logistic regression can also be viewed as approximations to this empirical risk minimization. So we define the hypothesis class. So this concept, this big H, will make reference to a hypothesis class, which is basically a set of hypotheses. And in this case, it's a set of classifiers that will be considered as part of this group. So for linear classification, this hypothesis class is defined as all the hypotheses that will give a 1 or a 0, depending if the dot product is larger, equal or and larger than 0. And in this case, we are considering theta to be a vector of m plus 1 elements, dimension m plus 1. And this is the set of all classifiers X, where the decision boundary is linear. So this would be a mathematical way to define all the set of hypotheses that are linear. So if we were studying, for example, nonlinear models such as neural networks, then we could let this hypothesis class H to be the set of all classifiers representable by some specific neural network architecture. Like, for example, suppose that we say our hypothesis class will include all those neural networks that have 3 neural layers, for example, with 3 layers. So at that moment, we will be specifying a hypothesis class. If we say, let's consider all the neural networks with 5 layers, then this is another hypothesis class. Empirical risk minimization can now be thought of as a minimization over the class of functions H in which the learning algorithm picks the hypothesis H circumflex. So empirical risk minimization, if we are considering this set of hypotheses, consists in searching for the hypothesis that will minimize the error in our training set. And all these hypotheses will belong, or all the hypotheses that we need to analyze belong to the hypothesis class big H. So we can analyze this empirical risk minimization when we consider a hypothesis class with finite number of hypotheses, like in this case. Suppose that we have a hypothesis class with only k hypotheses. Thus, H is just a set of k functions mapping from x to 0 and 1, and empirical risk minimization selects the H that will minimize the error in the training set. To give some guarantees on the generalization error, we will first show that the empirical error of this H is a reliable estimate of the generalization error. So here you see the epsilon circumflex, which is the empirical error, the error with the training set. And here you see just epsilon, which is the generalization error. So this is the error that you would expect your model to have when you classify new points. So we need to show first that this empirical error is a reliable estimate of the generalization error. And second, we need to show that this implies an upper bound on the generalization error of the best hypothesis that we can find with our training set.